So in the MCAT, you cannot use a calculator. So I think the key to understanding how to solve math without a calculator is repetition. Doing practice and seeing examples over and over again, and eventually you'll see the patterns. So let's do an example. 10 to the 7 times 10 to the 2. Simply 10 to the 9. This equals 10 to the 9. How about 10 to the 4 times 10 to the 3? This simply equals 10 to the 7. How about 10 to the 4 times 10 to negative 1? Simply this equals 10 to the 3. 10 to the negative 4 times 10 to the negative 2? This is simply 10 to the negative 6. So hopefully you can see the pattern. You simply take the exponents and you add them, and that gives you your answer. So pretty straightforward. However, what if we're dividing exponents? How, like 10 to the 7 divided by 10 to the 4? Well, this will equal 10 to the 3. How about 10 to the 3 divided by 10 to the 1? This equals 10 to the 2. So hopefully you see the pattern. You take the top exponent and you subtract it by the bottom exponent. And that gives you your exponent. 7 divided minus 4 equals 3. So what about this example? 10 to the negative 4 divided by 10 to the negative 2. Well, again, you take the top exponent and you subtract it by the bottom exponent, negative 2. And we know the rule, you do change, so this simply is negative 2. So now we know the answer. This equals 10 to the negative 2. So about 10 to the negative 5 divided by 10 to the 2. Well, again, you take the top exponent and subtract it by the bottom exponent. So negative 5 minus 2 is negative 7. So this equals 10 to the negative 7. So again, pretty straightforward. And again, with repetition, eventually it becomes second nature. So what about something like this? Well, when I see these examples, I break it down into components. So first, I focus on this guy. 10 to the 3 times 10 to the 4, we know this equals 10 to the 7. So first, focus on this guy, 10 to the 7, and we know we have this 10 to the negative 2. So this we know equals this. And we can't forget about this 10 to the negative 2. And we know how we solve this. We take the top exponent and subtract it by the bottom exponent. And you can't forget these signs. But again, top exponent subtracted by the bottom exponent. So again, we know change. So that's 9. So this equals 10 to the 9. So what about this example? Again, I like to break it into components. First, focus on this guy. So this we know is 10 to the negative 6. We know we add these guys. We add the exponents. So now we know this equals 10 to the negative 6, but we still have this guy down here. And we know how we do this. We take the top exponent and subtract it by the bottom exponent. So again, negative 6 minus 3 is negative 9. So now we know this equals 10 to the negative 9. So again, with repetition, hopefully eventually this starts to make more sense. So what if we have an example like this? 2 times 10 to the 7 times 4 times 10 to the 2. Well, the way I like to do this is I like to first focus on these little guys before I focus on these powers. So first I like to focus on these little guys. So 2 times 4 we know is 8. So we know this equals 8. So now we take care of these little guys. Now we can focus on these big guys. So we know if we're multiplying these two guys together, we know 7 plus 2 is 9. So we know these guys is essentially equal to 10 to the 9. So now we have our answer. Again, I like to focus on the little guys, take care of those guys first, and then I like to focus on these big guys. And we know how to solve those big guys, so now we know our answer is 8 times 10 to the 9. Because we know this, the way multiplication rules work, this is essentially the same thing as 2 times 4 times 10 to the 7 times 10 to the 2. We know this is essentially, these are essentially, they represent the exact same thing. So again, I like to focus on the little guys, take care of that, get that out of the way so we know that equals 8, and then we can focus on the big guys. So that's how I like to solve these problems. So how about 4 times 10 to the 3 times 5 times 10 to the 2? Well, again, first I like to focus on the little guys. So 4 times 5 we know is 20. So now we've taken care of the little guys. Now we can focus on the big guys. And we know how we take care of these big guys. We simply add these exponents. So this equals 10 to the 5. 3 plus 2 is 5. So again, when you're multiplying exponents, you add the exponents. But instead of 20 times 10 to the 5, we know this is the same thing as 2 times 10 to the, we divide this by 10, so we multiply this by 10 to the 6. So we know 20 times 10 to the 5 is the same thing as 2 times 10 to the 6. And sometimes instead of having a double digit out here, sometimes you need to break it down into a single digit. But again, we know these are the exact same thing. And essentially what we're doing is we take this guy and we divide it by 10. And we can do that. We can take this guy and divide it by 10 as long as we take this guy and multiply it by 10. We're dividing this guy by 10, and we're multiplying this guy by 10. And we can do that because, again, we know dividing this guy by 10 and multiplying this guy by 10 is the same thing as multiplying this by 10 divided by 10. Because, again, that's essentially the same thing, and we know 10 divided by 10 is simply 1. So that's like multiplying this guy by 1, which is making no difference. So again, if we multiply this guy by 1, it's causing no change, so we're not changing the number. But instead of having 10 divided by 10, we know we take this guy and divide it by 10, so that's taking care of this guy, and this guy multiplying by 10, and that's essentially multiplying this guy by 1, but again, we're just breaking it down in a way so we have a single exponent. And again, with time, this will get easier. But the point is, we divide this guy by 10 and we multiply this guy by 10 and we're causing no change. And now we have a single digit in our bottom part. So again, what if we have this problem? Well, again, I like to focus on these little guys. And then once I figure out these little guys, then I can focus on the big guys. So we know 2 divided by 8 is simply 0.25. 2 divided by 8 is 0.25. So we take care of that guy. So again, but we still have these exponents. So again, take care of this little guy, but we can't forget these exponents, but we know how to take care of this. We take the top and subtract it by the bottom. So 4 minus -2, the top subtracted by the bottom. And again, you can't forget this was a negative. So again, that's just 6. So again, we know this is essentially equal to 10 to the 6. So now we know this is equal to 0.25 times 10 to the 6. And again, we know we can multiply this guy by 10 as long as we divide this guy by 10. So that's 2.5 times 10 to, so again, multiply this guy by 10 as long as we divide this guy by 10, so that's equal to this. So this is the same thing as this. And now we have a single digit in this bottom part. But again, as long as we multiply this guy by 10, we can do that as long as we divide this guy by 10. So therefore, we're essentially causing no change. We're multiplying this by 1, essentially. So what about this example? This example looks a little complex, but it's really not so bad. Again, first, I like to focus on this. So 1600 divided by 2 is simply 800. So we take care of that guy, but again, we still have these exponents times 10 to the -6 divided by 10 to the -1. And we know how we do this. We take the top and subtract it by the bottom. So again, top subtracted by the bottom, this bottom. Then again, we know change, so that's essentially -5. So we know this is essentially 10 to the -5. But again, sometimes instead of this digit, again, we can change this to essentially we can divide this guy by 100, which would give us 8, and we can do that as long as we multiply this guy by 100, which would be 10 to the -3. So this is the same thing as this, and now instead of 800, now we have a single digit. So again, as we can divide this guy by 100 as long as we take this guy multiplied by 100. Because again, dividing this by 100, as long as we multiply this guy by 100, we're essentially doing no difference. We're causing no difference. And again, so this is something that with time, I know this may seem a little overwhelming, but with time, this becomes second nature, and you'll get good at it. And it will save you precious time in the MCAT. So I recommend doing practice, maybe watching this video again and doing this practice. So what about this? This may seem a little complex, but it's actually really straightforward. What I like to do is first, instead of focusing on these magnitudes, first I just focused on the 2 and the 3. And I multiplied 2 by 3. So 2 multiplied by 3, we know, is 6. 2 times 3 is 6. So that's the first thing I do. Then I focus on the magnitude. So we know when we had this 2, we know we had 1, 2 magnitudes to the left. And when we had this 3, we did 1, 2, 3, 4 magnitudes to the right. So 2 to the magnitudes to the left, 4 magnitudes to the right is equal to 2 magnitudes to the right. So 2 magnitudes to the right. So now we have our answer. So now we know our answer is 600. So let's do another example. Again, first, I like to focus on these single digits and do 3 times 6, which we know is 18. 6 times 3 is 18. And then once we've taken care of that, then I like to focus on the magnitudes. So we know when we had the 6, we essentially had 1, 2, 3, 4 magnitudes to the right. When we had the 3, we did 1, 2, 3 magnitudes to the left. So 4 to the right, 3 to the left is equal to 1 to the right. So this is 1 to the right. So now we have our answer. So now we know this is equal to 180. So what about this example? Well, this you should know. Essentially, if you have 82,000 divided by 100, you simply just can cancel out the magnitude. So to get rid of this magnitude and then get rid of this magnitude. So we know this is equal to 820. So again, that should be straightforward. So what about this guy? Well, there are lots of different ways you can solve this guy, but the way I like to do it is first I like to pull out the 4 here. I like to pull out the 4. So that would give us 4 times 100,000. So instead of dealing with 400,000, I like to pull out the 4, which would give us 4 times 100,000. And we know 4 times 100,000 is 400,000. So that's the first thing I do. Then on the bottom, I like to pull out the 2. So pull out the 2. 2 times 10. So again, we know that equals 20. Now that we've done this, we can, again, 4 divided by 2, we know simply 2. So this is the same thing as 2. And again, we're multiplying that by 100,000 divided by 10. And we know with magnitudes, we can simply cross out the magnitude. So we know this is equal to 2 times, essentially, we see we have 4 zeros. We have 4 zeros. So now we know, and we know clearly this is equal to 220,000. So again, that's the way I like to do this. But again, with time, I promise, with time, you'll be able to do this very quickly. And trust me, with time, you'll get good at it. And you'll be able to do it at lightning speed. And it will really come in handy. So what about another example? What about something like this? Well, in certain contexts, I like to switch it to scientific notation. So we know this is equal to 6 times 10 to the negative 3 divided by 2 times 10 to the negative 2. We know these are the same thing, and this is the same thing. And now, again, we know 6 divided by 2, that's simply 3, so that takes care of this guy. And now this guy, we know how we solve this. We take the top and subtract it by the bottom. So change, so that's negative 1. So we know this is 3 times 10 to the negative 1. Take care of this guy first, that's 3. And then take care of this guy. So that's negative 1, so now we know our answer. So now we know what this is equal to. So now let's do some other examples. So the key to the MCAT is knowing how to make estimate numbers rather than dealing with these specific values. So instead of 0.058, we know we can estimate, and we know this is essentially 0.06. These are essentially the same thing. And what about 2011? This is essentially the same thing as 2000. And notice we're taking this guy estimating up. So if we estimate up, the other guy we should estimate downward, as long as we're multiplying 2 terms. So now we know how we solve this. First, focus on the single digits. So 6 times 2 is 12. So that's the first thing we do. And then focus on the magnitude. So when we had the 6, we did 1, 2 to the left. When we had the 2, we had 1, 2, 3 to the right. So 3 to the right, 2 to the left equals 1 to the right. So 1 to the right. So now we know our answer is 120. So what about another example? So again, in this example, I like to, again, focus on this 18 and this 2. So 18 times 2, we know, is 36. So that's the first step. And now we can focus on the magnitude. So again, remember, the 2 numbers we were multiplying were 18 and 2 to get our 36. So therefore, we're interested in the 18. So in the 18, how many magnitudes from this 18 standpoint? So 1, 2, 3 to the right. And then this 2 is what we're interested in. So for 2, how many magnitudes? So 1 to the left, so 3 to the right. 1 to the left is the same thing as 2 to the right. So 1, 2. So now we know our answer is 3,600. So what if we get something a little more tricky like this? So again, what I like to do is first, we know 1 divided by 1.6. That's a little tricky. How do we do that? So I'll just do that as 1 divided by 1.6. So again, not really sure how we'll take care of that, but we know how to take care of this guy. We know we take the top and subtract it by the bottom. So 7 minus negative 3 would be 10. So this is times 10 to the 10. So we know this is this guy. We did no changes with that guy, but we know this is essentially 10 to the 10. So how are we going to take care of this? This seems a little complex. Well, we can make an estimate. So again, instead of dealing with this guy, we can deal with 1 divided by 1.5 times 10 to the 10. So again, it's the same thing except 1.6, we change to 1.5. Why do we do this? Well, we know 1.5 is the same as 3 divided by 2. So instead of 1.5, we can change this to essentially 1 divided by 3 divided by 2 times 10 to the 10. So again, all we did was instead of 1.5, we changed it to 3 divided by 2. And we know the way fractions work, we do the reciprocal when throwing it upstairs. So when we have something in the denominator, a fraction in the denominator, we do the reciprocal when we throw it upstairs. So that's the same thing as 2 divided by 3 times 10 to the 10. This is the same thing as 2 divided by 3 because we take this guy, we do the reciprocal when throwing it upstairs. So now we have 2 to the 3. And we know 2 to the 3 is 0.66. 0.66. So we know this is 0.66. And then we still have this guy, so we can't ignore this guy. So again, instead of 2 divided by 3, we have 0.66. And we know normally we would like to do 6.6. We like to have it as a single digit. So we multiply this guy by 10. And we're allowed to multiply this guy by 10 as long as we divide this guy by 10. So that would be 10 to the 9. So now we have our answer. So now we know this guy, which again seemed really complex, this 1 divided by 1.6, which seemed really complex with doing estimates. Now we know this is essentially 6.6 times 10 to the 9. And you can take this and throw it in the calculator, and you would essentially get 6.6 times 10 to the 9, which would be a close enough estimate. So what about something like this? This may seem really complex. Well, again, the way I would do this is do this as 1800 divided by 9 divided by 2, because we know 4.5 is the same thing as 9 divided by 2. Now we know if we have a fraction in the denominator, we do the reciprocal when throwing it upstairs. So that's 2 essentially divided by 9 times 1800. So again, we take the denominator and do the reciprocal when throwing it upstairs. So now we have 2 divided by 9 times 1800, which we can also write as 2 times 1800 divided by 9. So now what we can do is, again, instead of dealing with 1800, I like to pull out the 18. So if we pull out the 18, we have 2 times 18 times 100 divided by 9. So again, this is the same thing as this guy. And we did no changes with this. So why do we do this? Well, we know 18 divided by 9 is 2. So we know this could be reduced to 2. So if we reduce this to 2, we would essentially have 2 times 2 times 100. Because again, we essentially have replaced this with 2, which is replaced with that, and then these guys stayed the same. So now we have this, which is essentially 4 times 100, which we know is 400. So now we know this guy is 400. So again, I know this may have seemed like a lot of arbitrary steps, and it may have seemed random, but I promise, do practice examples, and you'll get really good at this, and you'll be able to do this as fast as you can write it. You'll be able to do this math as fast as you can literally write it down. So I promise with time it gets better. So what about something like 7 divided by 5? So sometimes it's these simple guys that trip me up and can be challenging. But what I like to do is 7 divided by 5. What we can do is we can multiply the top and the bottom by 10. So that would give us 70 divided by 5. So again, multiply the top by 10 and multiply the bottom by 10. So now we have 70 divided by 50. And we know we can do that. We can multiply the top by 10 as long as we also divide the bottom by 10. Again, we're essentially, as long as we multiply the top by 10, we can multiply the top by 10 as long as we multiply the bottom by 10, because that's essentially multiplying this entire thing by 1. So again, and if we do that, we're causing no change. So we multiply the top by 10 and we multiply the bottom by 10. So now we have this guy. Now what we can do is we can multiply the top by 2 as long as we multiply the bottom by 2. Because again, we're causing no changes. If we multiply the top by 2 and multiply the bottom by 2, we're doing no changes. So when we do that, we're essentially left with 140 divided by 100. So now we know with our magnitudes, we can cancel the magnitude, and then we cancel another magnitude, so put one magnitude. So again, this is essentially 1.4. Again, we cancel the magnitudes, and now we essentially have 14 divided by 10. So dividing anything by 10 is just one magnitude. So now we have 1.4. So now let's do another example. 9 divided by 2. Well, again, what we can do is we can multiply both sides by 10, multiply top and bottom by 10, so we have 90 divided by 20. Now what we can do is we can multiply the top and bottom by 5. So multiply the top by 5, we get 450, and multiply the bottom by 5, we get 100. Now we know we can just cancel the magnitudes. Cancel one magnitude, and then 45 divided by 10, cancel another magnitude. So now we have 4.5. And this you should get better with time, just knowing 450 divided by 100, we know is simply just two magnitudes. So this may have seemed really random, and what is going on? Well, there's actually a method to the madness. What we do is when we have a tricky fraction like this, we need to make the bottom fraction either 10 or 100 or 1,000. For example, with this guy, if we were to take the denominator and turn it into 100, now we can simply just deal with magnitudes. 1, 2 magnitudes. We have 100, so we know we can cancel 2 magnitudes. So now we have 1.4. When we have 9 divided by 2, again, as long as we can make the denominator either 10, 100, 1,000, 10,000, as long as we can take the denominator and turn it into either 10, 100, 1,000, whatever, then we can just start canceling out the magnitudes. So this is 100, so that's 2 magnitudes, so now we have 4.5. But sometimes it's a little harder. What if we have 8 divided by 3? We know if we can make this bottom 10 or 100 or 1,000, then we can simply take the top and just cancel out those magnitudes. But in this example, it might be a little harder. For example, we can multiply the top and bottom by 3. So 8 times 3 is 24. 3 times 3 is 9. So we're close to 10. We're not quite as 10. So now what we can do is we can increase this by a little. Increase this to 10. And it's okay. We can increase this guy by a little as long as we increase the top by a little. So maybe to 26. So again, we know with a fraction, as long as we increase both by roughly the same amount, we're causing no change. So this is where estimation really comes into handy. In practice, you'll get better. But I promise, do these estimations and you'll see the answer really isn't changing as much as long as you're being careful. Like this guy, we increased by about 10%. So this guy we would have to increase by about 10%. So again, the point is, now what we've done is instead of this, we have something that's roughly the same, but now we have a 10 in the denominator. So now we can get rid of 1 magnitude. So now we know this is roughly 2.6. So now we know this is roughly equal to 2.6. So again, pretty straightforward. And again, with time you'll get better at this. So again, with time you'll get better. So again, when we have these exponents that we're multiplying together, we add these exponents. So we did in the beginning of the video, we did this. So we know this equals 10 to the 5. And what about this? We know we add these exponents. So this is equal to 10 to the 4. We simply add these. But what if we have an exponent to a power? For example, 10 to the 2 to the power of 3. So when you have an exponent to an exponent, then you multiply those values. So this would be 10 to the 6. You would multiply these values. So what about 10 to the negative 2 to the 6th power? Well, again, in this example, you would multiply these powers. So that would be 10 to the negative 12. So notice the difference. When you multiply these powers, you add them. So this would be 10 to the 5. When you put a power to another power, you multiply them. So I know it's a little tricky, but with time, there really aren't that many rules you need to know to do the math for the MCAT, but this is just one of them. So again, when it's a power to a power, you multiply them. So now we know 10 to the negative 2 to the 6th power is equal to 10 to the negative 12. So something else important to know is when we have some kind of expression to a power, when you take that power, you need to essentially pass on that power to each part of that exponent. So again, you would give that power to each part. So we would have 6 to the 2, so give that 2 to the 6, and also give that 2 to the 4. And we know when we have a power to a power, you multiply them, so that would be times 10 to the 8. So now we know this is equal to 6 times 10 to the 8. And I promise, a mistake that people commonly make is they'll see something like this. And instead, they'll simplify this by doing 6 times 10 to the 8. They'll remember, oh, this is 2 to the 4, so multiply these, but they'll forget to take that 2 and also to give it to the 6. The 6 is also impacted by that power. So again, I promise this is a mistake people make commonly, but you need to know, whenever you have some kind of expression to a power, that power affects everything in that expression. So again, it goes to the 6, so that's 6 squared. Then again, a power to a power, we know we multiply those, so that's to the 8. So now we know, which again, we know this would be 36 times 10 to the 8. And again, we know we can divide this by 10 as long as we multiply this by 10. So really that's 3.6 times 10 to the 9. So what about this guy? Again, when you have some expression to a power, you need to take that power and to give it to all the parts of the expression are affected by that power. So this would essentially be 2 to the 3 times 10 to the 2. 10 to the 6. Because again, when you have a power to a power, you multiply them. So now we know this is equal to this. So what if we have something like this? Well, again, remember our rule. When we have some kind of expression to a power, everything in that expression feels that power. So you would give this 2 to the 5 and you would give this 2 to the 2. So again, you know when you have a power to a power, you multiply them. So this would be 10 to the 10 divided by 10 to the 4. So again, each expression feels that power. So that's just a kind of a general rule to know when you have some kind of expression to a power, everything in that expression feels that power. So again, remember we multiply anything to a power, you multiply it. So 5 times 2, that's the 10. 2 you multiply them, so that's 2 to the 4. And also maybe if you had this 10 to the 5 times 10 to the negative 2. So again, remember, when you have something in the denominator of minus power, when putting it in the numerator, you just switch the sign. So this would essentially be the same thing as 10 to the 2 times 10 to the 5. This is the same thing. Whenever you have a power in the denominator, when you throw it upstairs, you just change the sign. For example, what if we had something like this? 10 to the negative 2 divided by 10 to the 5. This is the same thing as 10 to the negative 5 times 10 to the negative 2. So that's just another rule. When you have something in the denominator, when you throw it upstairs, you simply just change the sign. So instead of 10 to the 5, throwing it upstairs is 10 to the negative 5. So that's another rule. Again, these are just some rules you really need to know while doing the MCAT. So what if we have an example like this? Well, again, whenever we have an expression to a power, remember, everything in that expression feels that power. So everything would feel the power. So that would be 2 to the 3 times 10. Remember, to the 12, remember a power to a power, you multiply them. And then this would be 10. Again, 3 to the 3. So you multiply them, so that would be to the 9. So we know this would be equal to this. And again, we could take this 10 to the 9 and throw it upstairs as 10 to the negative 9. And then again, we would get rid of this, and now we would have our expression. So, or now we would see what this is equal to. So now once we have what this is equal to, how do we solve this? Well, again, we know how we do this. This is essentially 2 to the 3, which we know is 8, times, and we know how we solve this. We essentially just add them. So if we add them, that's to 10. That would be 10 to the 3. So now we know this is equal to 8 times 10 to the 3. And again, something to remember. If, for example, we have 8 divided by 2 to the second power, we know everything feels that power. So the 8 would feel the power, and the 2 would feel the power. So again, remember, when we have any expression to a power, everything feels it. But again, exactly how you can divide that power, how each thing feels that power, you can also go in the reverse direction. If you have 3 to the 2 divided by 4 to the 2, you can pull out that power to both of them to give 3 divided by 4 to the 2. So again, you kind of, on both of them, you pulled out that power and you have this. And we know that makes sense. That should make sense because we know if we have this expression, we could give the 2 to both of them to have this guy. So it makes sense we could go in the reverse direction to pull out the 2 of both of them to have this guy. So again, I know it may seem like a lot right now, but I promise with time, this gets better. Maybe watch this video again and try solving these on your own. And again, with time, it gets better. So what if you were to ask, what is 15% of 320? I remember if you were to ask me, how do you find 50% of 320? I would have no idea how to do this, but it's actually really not so bad. So we know 10% of 320 is clearly 32. Because again, 320, so 10% would be 32. So therefore, clearly 5% would be 16, which is again just half of 32. If we know 10% is 32, we know 5% must be 16. So therefore, we know 15% must be these. If 10% is 32, 5% is 16, you can add these, so that would be 48. So now we know 15% of 32 is 48. So it's pretty straightforward. It's not so bad. Usually when you ask for some percentage or something, first find out what 10% is. And that's easy. That's just one. So first find what 10% is. And from that 10%, you can find out what 5% is. You can find out what 20% is or 40% from that 10%. So let's do another example. What if we're asked for 35% of 300? Well, again, we know 10% is 30. So therefore, 5% is 15, because if 10% is 30, 5% is 15. So therefore, we know 30% would be 90. 10% is 30, so 30% would be 90. And we know 5% again is 15, so 35% would clearly be 105. So 35% of 300 is 105. So again, when you have one of these problems, first find out what 10% is, and from that 10%, you can find out everything. So now, lastly, let's do logs. So I know lots of people don't like logs, but logs are actually super easy. Log to 1,000 is simply 3. You simply just find out how many zeros there are. 3 zeros, so log to the 1,000 is 3. Log to the 100,000 is 5, because again, we have 5 zeros. And really, a better way to look at it is 1, once we have 1, how many magnitudes? 1, 2, 3, 4, 5 magnitudes. So that's what log is. Logs essentially tell, when you take the log of 100,000, you're asking how many magnitudes are there? There's 5 magnitudes. 5 magnitudes. So again, log to the 10. Again, this is just saying how many magnitudes. There's 1 magnitude, so pretty straightforward. Then again, when you have a value that's less than 1, again, this would be how many magnitudes? 1, 2, 3 magnitudes to the left, making this smaller. So this would be -3. What about this guy? This is 1, 2, 3, 4, 5, 6 magnitudes to the left. So this would be -6. And again, the way I like to do it is I kind of like to think of a number line, where again, focusing on 1 and think how many places are you moving? So 1, 2, 3, 4, 5 directions in the positive direction. So this is +5. How about this guy? Again, I like to focus on 1. First, just focus on the 1 and see. 1, 2, 3 to the left. So that's -3. 3 magnitudes in the minus direction. What about this guy? Again, 1, 2, 3, 4, 5, 6 magnitudes in the minus direction. So that's -6. This guy, 1 magnitude in the minus direction. So that's -1. So logs are easy. Logs are pretty easy. So don't get caught up on these logs. And what about if we have negative log to the 1,000? Well, again, it's essentially the exact same answer, except at the last minute you throw in a minus sign. So again, we look. This is 1, 2, 3 to the positive direction, so that would be +3. But because we have a negative, this is -3. So this negative just essentially, it's the exact same thing, except you flip the sign. So pretty straightforward. So what about this example? This is 1, 2, 3. So that's -3. So that's, remember, 1, 2, 3 magnitudes in the minus direction, so that would be -3, but because it's negative, you flip the sign, so it's +3. So logs are straightforward, and just know log to the 1 is 0, because we have no magnitudes. We're moving no magnitudes, 0 magnitudes to the right or left. So again, that's 0. But you won't always see it in this form. Sometimes you'll see it in these fractional forms. Well, but again, it's the same idea. It's the same idea. It's again, you could really just ignore this 1 and just see 1, 2, 3, 4, 5 in the positive direction, so this is +5. And then again, we know we could just turn this into a decimal form and then find what it is, or you can see in the denominator how many fractions there are. But again, these logs are pretty straightforward. Just kind of memorize this table, and then again, when you have the minus sign, again, it's really, at the end of the day, when you have a minus sign, it's the exact same thing. Just at the last minute, you change the sign. And remember, also what you can do is, for example, if you have negative log to the 1 divided by 100, that's the same thing as log times 100 divided by 1. Essentially, when you have a minus sign, you can essentially get rid of that minus sign as long as you invert the fraction. So again, another example, maybe we have negative log to maybe 1,000. That's the same thing as log to 1 divided by 1,000. So again, when you have a minus sign, you can get rid of the minus sign as long as you invert the fraction. So again, for maybe like this example, this is the same thing as log times, again, we have 6 zeros. So 1, 2, 3, 4, 5, 6. So again, it's the same thing. So if you like, you can simply get rid of that negative sign as long as you flip the fraction. Then we know you count 1, 2, 3, 4, 5, 6 magnitudes in the positive direction, so this equals +6. So again, logs should be your friend. Logs aren't hard. And then when you have scientific notation, this is extremely easy. Log to the 10 to the 5, simply just 5. It's simply that easy. Log to the 10 to -3, this is simply equal to -3. Log to the 10 to -6, this is simply equal to -6. And then when you're dealing with a negative log, it's the same thing. You take this which we know this would be 3, but because there's a negative, you now it's -3. So again, just it's the same thing. You can focus. It's the same thing, but at the last minute, throw in that negative sign. So again, logs are easy. So what if we have something like this? Log to the 2700. Well, again, the way I like to do this is I like to create a range. So again, what I do is just focus on this first digit. Don't worry about the 7. Just focus on this first digit. And on this first digit, do one example with the 1. And then that first digit, do another example where that first digit is now 10. So again, focus on that first digit. We see we have 3 magnitudes. So again, see those 3 magnitudes. But on that first digit, have a 1. And then on that first digit, have a 10. So now we know our answer is between these two values. We know this log to the 2700 is between log to 1000 and log in 10,000. So again, we know our answer will be between these two guys. And we know log to 1000 is simply 3. We know log to 10,000 is simply 4. We again count the magnitudes. So again, so we know this is equal to something between 3 and 4. And really the answer, I believe, is 3.4. I believe the answer of this is 3.4. But the point is, when you have something like this, again, just focus on that first digit. Everything else just turn into a 0. Don't worry about all these other digits. Just focus on the first digit. Do 1 as a 1. Do another as a 10. And then solve these and know your answer will be in between. So the answer for this is in between these two extremes. So not so bad. So let's do another example. Log to the 540. Again, don't worry about these other two digits. Just focus on the first digit. Focus on this first digit and make these zeros. So we would have 2 zeros. So we would have these 2 zeros. So again, just turn these guys into zeros and just focus on this first digit. Do 1 as 1. And do the other extreme as 10. So now we know our answer is between these two answers. So again, we know this is clearly 2, this is 3. So now we know this answer will be between 2 and 3. We know log to the 540s, but it will give us is an answer between 2 and 3. So again, the point is when you have one of these examples, just do the extremes. Find these kind of extremes, and you know the answer will be in between. And again, the point is, do 1 and 10, between 1 and 10. For this magnitude of the thousandth place, do 1 and 10. And then find those values and you know your answer will be in between them. But sometimes it'll be a little more tricky. For example, a typical question you'll see is what is the pH of a solution when the hydrogen ion concentration, the hydronium ion concentration is 2.7 times 10 to the negative 5. So we know the way you find the pH is you take the negative log of the hydronium ion concentration. So we would have to do the negative log of this hydronium ion concentration. So this is a typical question you'll see. So how do we solve this? Well, again, what I like to do is, again, take this guy, and again, now we have the magnitude, so that's taken care of. But instead of 2.7, try 1 as 1. And then do the other extreme as 10. So again, that's the way I like to do it. Again, the point is these magnitudes, remember the magnitudes, just leave alone. Just leave alone, that's not important. It's this first digit that's important. And then do 1 as 10, and then do 1 as 1, and then do 1 as 10. And now we know our answer will be in between these two values. And again, instead of doing 10 to the negative 5, we know this. We can divide this by 10 as long as we multiply this guy by 10, which again is a rule we already explained. So that's the same thing as this. So we know. So now we can solve both of these. So we know. Remember, with logs, with these scientific notation, this is easy. We simply just take this value. So that's negative 5. But again, because it's negative, we change the sign. So now it's positive 5. And then again, with logs with scientific notation, we simply just take what this value is. So that's negative 4. But because it's negative log, we have to change the sign. So that's positive 4. So now we know this value is between 5 and 4. So again, the point is you take this for the magnitudes. You again remember what we did with this guy because our rule. But again, the point is we leave these guys alone, and then we find these two extremes, and then we do 1 as 1, and we do the other as 10. And then with practice, hopefully you should get better at this, and with time, hopefully starts to make a little more sense. So again, maybe